The next item here is the integration of the given function f of z equal to z along a vertical line segment from 3 to 3 plus 4i. Take note that the path here is a vertical line segment. Hence, we're going to use here the parameterization of the path for vertical line segment. To start, let us not forget that the integral of f of c dz along your certain path, in this case the vertical line segment, is equivalent to the integral of f of z of t times the first derivative of z of t with respect to t from a to b. We need to identify z of t so that we can also get the z prime of t, and later on use the idea of identifying the a and b values for our integration. Take out our path is a vertical line segment. Previously, we've known that the parameterization of a vertical line segment is identified as k plus I t. It's a vertical line segment. Looking at it in an argand plane, complex plane, you can see that if it's a vertical line segment, the value of x do not change. That's why here, for the real part, which stands for x, for our z definition, x plus iy will not change. It's constant k. Okay? So we can actually get our k here for our z sub 1 being 3 and our z sub 2 being 3 plus 4i. Our z sub 1 does not have any value or term for imaginary unit. But of course, you can always write it as plus 0i. We can obviously see that our points are actually on the vertical line as our k do not change. That's the value of x. Obviously, that's the k equivalent to 3. And you would also see that this portion here would actually be very helpful for us as we would like to identify a and b coefficients. A and b coefficients would be for the numerical coefficient of the imaginary part as it changes from 0 to 4. That would be our 0, the starting point, to 4. That's the movement of our function along the vertical line segment from these given 2 points. So we now have our a and b and our k. Actually, our a and b is not necessarily needed yet for our z of t, but it's later on. But for our z of t now, identified as k plus it, our k is a 3 plus it. This is a function of t. With that, we can actually solve now for its first derivative, treating all terms without t as constant. I'm talking about the first term of 3. So we are going to derive it with respect to t, that's 0. And when we take the derivative of it with respect to t, treating this as constant is simply I. This is equivalent to I. That's the first derivative of our z of t with the idea here for our function and its path. Of course, our z of t is here. Now, sometimes you might be, what they call this one, tricked to using that automatically here. Well, for this case, since our function f of z is actually z itself, of course, our f of z of t will also be the z of t itself, already identified as 3 plus it. Okay? So it's just as it is. However, take note, just for other situations, if this was z squared, it doesn't necessarily mean that whatever your function here, you can automatically substitute that for our formula. No, you still need to square that if it's z squared. That would mean squaring that as well. But since our given is already z, so we can have it as itself. So with this now, we can now continue with our target. The integral of f of z dz along the path is identified as the integral from a to b of your f of z of t times the first derivative of z of t dt. Let me use other color here. The integral, we know our a and b is 0 to 4, so 0 to 4. Again, our f of z of t is just itself 3 plus it, and the z prime is actually I dt. Okay? Now, when you look into this perspective, you might be tempted to distribute that. You may actually, but just for the inspection, since we're trying to solve for the integral of that with respect to t and I as a factor, not a term, but a factor in this given expression is a constant, you can always take that one out using the constant multiple property of integrals. Hence, you will have your I times the integral of 0 to 4 of 3 plus it dt. Okay? You can use here the linearity property. So you have here I times, then use here the integral. Linearity property tells us that we can actually have this 3 integral of 0 to 4 dt. We discuss also the properties, right? Right? So you have 0 to 4 of dt plus your constant I, an integral of 0 to 4 of your t dt. Okay? And you can just simply move into the specific form of that. But here comes one thing I would like to emphasize. Of course, you can always do this. You can continue doing even that. And you will still get the same answer as mine, as I will introduce another method here. Now, allow me to erase all of that. Okay? So take note of that. You can screenshot this, or you can actually stop into this one and think of what I am trying to say earlier. But you can let me try to erase all of this and return to the first form here. Now, if I'm going to let, here comes one technique you can do. If I'm going to let u, or let's say u as 3 plus it, what is its first derivative with respect, what is its first derivative? Okay, so with respect to t, that's 0 plus I dt, right? Or simply I dt. That's your du. This is actually this one here. And your u is this. In short, this is already in the form of u du. Okay? So what is the use of that? If we're going to have u du, then the integral of this, the integral of u du, is just equivalent to u to the power of n plus 1 over n plus 1, right? So our n is actually identified here as 1, okay? So that's 1. So 1 plus 1, basically that's u squared over 2, okay? So where n is equal to 1. So basically, if we're going to have it this form, your u earlier was 3 plus it u squared. So you will have your 3 plus it squared over 2 with this with the boundary of 0 to 4. Okay? If we're going to continue the process I mentioned earlier, I believe you will still get the same answer. You can try that on your own, but let me stick to this, as I'm going to have here the next answer. You have 3 plus I times 4. I'm going to square that over 2 minus, you will have here 3 plus I times 0. You're going to square that over 2. This is equivalent to 3 plus 4i squared over 2 minus 3 plus 0, or you will have here 3 squared over 2. Now, 3 plus 4i squared is actually the result when multiplying that said binomial expression to itself. 3 times 3 is 9. Inner term is 12i. Outer term is 12i. You have here plus 16i squared. Take note that I squared is negative 1. This is equivalent to 9 plus 24i minus 16. Because I squared is negative 1. This is actually negative 7 plus 24i. That is the value of your numerator here. Negative 7 plus 24i over 2 minus 9 halves, which will give us a final answer of negative 16. Not yet the final answer, over 2. Factoring 2 in our numerator, you have negative 8 plus 12i over 2. So canceling that, your final answer is actually negative 8 plus 12i. This is the integral of the given function, okay, along the vertical line segment, using the parameterization of that, using all of these processes and this idea here. Again, you can continue doing what I did earlier. I believe you will still get the same answer, and hopefully you will still get the same answer as mine. Thank you very much for watching.